Hello and welcome to my video on the lab experiment that I conducted, which was M1 focused on the resistivity measurement of the semiconductors by a four-probe method. So the objective of our video was to determine the resistivity of the semiconductor materials by using a four-point probe and to determine the energy band gap that is present in the semiconductor material. The apparatus that we used in our experiment included the four probes arrangement, germanium, an oven, a four probe setup, and a thermometer. Moving on to the procedure part of the experiment, we set the germanium sample onto the four probe arrangement's base plate. The tubing carrying the probes was then gently tightened to ensure adequate electrical contact. We used minimum pressure and we exercised extreme caution when handling the germanium crystals. We then connected the inner pair of the probes, the yellow and green ones, to the probe voltage terminals and the outer pair of the probes, the red and black ones, to the constant current power source. We then placed the four probe setup inside the oven and secured the thermometer using the provided hole. We then turned on the AC main supply for the four probe setup and chose the current measuring mode on the digital panel. We then sent the current to a desired amount, which in our case was 4.6 milliamperes. Furthermore, we then set the voltage measuring mode on the digital panel meter. The voltage between the probes were then read. We then connected the oven power supply and switched it on, recording the measurements for increasing temperatures for every 10 degrees Celsius up to 140 degrees. We then measured the distance between the probes and the crystal thickness. We switched off the oven and recorded the voltage for decreasing temperature next. In this part of the video, we will look at the data that we collected throughout the experiment. On the left-hand side, you can see that we found the distance between the probes, which was 2 millimeters, the thickness of the crystals, which was 0.5 millimeters, and the current we used was 4.06 milliamperes. We also tabulated the data, which included the temperature, the increasing temperature, the voltage that we had, the resistivity that we found by using the equations given to us, ln P, which is ln resistivity, and 1 by T, which we will use to graph the data. We have also found the same data for the decreasing temperature, as you can see on the right-hand side. Using the data from the previous slide, we have further tabulated the data for the analysis of the increasing temperature part of the experiment. As you can see on the left-hand side, we have found the values of x, which is 1 by t, and y, which is ln p. We have then used these values to find xx, which is x squared, xy, mx plus c, y minus mx plus c, and y minus mx plus c squared, which we will find out why we have done so. Using the data in the previous slide, we found these further values. N, which represents the number of data that we had. We found the triangle, which was 4.6781. The m, which represents the gradient, was found to be 3.57115. And c, which represents the y-intercept on the graph of ln p against 1 by t, is 13.31395. We then found the values of sigma, which represents the uncertainties for each value. So sigma m, which is the uncertainty of the gradient, was found to be 0.1533, and for sigma c, which is the uncertainty of the y-intercept, was found to be 0.4204. As you can see here, we have plotted the graph of ln p against 1 by t for the increasing temperature part of the experiment. We now begin to analyze the data for the decreasing temperature part of the experiment. We have done the same thing as we did for the increasing temperature part, but the values of y are obviously different because the resistivity is different. We have again found x, y, x squared, and xy, as well as mx plus c, y minus mx plus c, and y minus mx minus c squared. Once again, using the data in the previous slide, we have found the values for the gradient, the y-intercept, the triangle, and the uncertainties for each value. As before, we have plotted the graph of ln p against 1 by t, but this time for the decreasing temperature part of the experiment. In this part of the video, we will try to answer some of the questions which were given to us in the lab manual. The first of the questions was, what is the advantage of a four-probe method over the other conventional methods? Well, the advantage is that we achieved a far more accurate result for the value of the resistance. This is due to the fact that the four-probe has a very little point of contact and spreads the resistance associated with the voltage probe. We were then asked, can we use an ordinary millivoltmeter instead of an electric millivoltmeter or potentiometer to measure the inner probe of the voltage, and why? While an ordinary millivoltmeter has a very small impedance and thus requires more current to operate it. The setup that we have provides a very small current, so this would not be suitable for our experiment. We were then asked to explain the behavior of the ln p against 1 by t graph and to calculate the energy band gap from these curves. Well, in the graph we plotted, when the temperature is higher, there is a linear region, but as it decreases, the curve begins to level off or begins to curve. Here you can see that we have used the gradient that we found from analyzing our data to find the energy band gap and the percentage error of the energy band gap as requested in the previous question. Finally, we were asked why a semiconductor behaves as an insulator at 0 Kelvin. Well, at 0 Kelvin, particles have zero thermal energy, and so the electrons do not have enough energy to jump from the valence band to the conduction band, thus acting as an insulator. Almost nearing the end, we will discuss some of the results and analysis that we have done during the experiment. We have clearly shown that the voltage does decrease when the temperature increases, thus showing that the resistance of the germanium decreases. This is because the increase in the temperature decreases the band gap, which allows electrons to conduct more easily. We also plotted graphs of ln p against 1 by t. At higher temperatures, both plots showed linear regions, but as the temperature decreased, it became more curved. We also received slightly different values for the energy band gap compared to the experimental values, which may have been caused by the inaccuracy of the equipment or some human error on our part. The percentage error for both our energy band gaps was 6.06 and 3.03 respectively, which is very slight, which verifies our data to be quite acceptable. In conclusion, we've measured the resistivity of the semiconductors using the 4-point probe method and also analyzed the values for a better accuracy, while also finding the value of the energy band gap for the increasing and decreasing parts of the experiment using the Arrhenius equation given to us in the lab manual. Here we have provided the references for the information that we used to make this video, and especially while answering the questions and writing the discussion. Thank you for watching our video, and we hope you have a very good day.